You are probably intimately familiar with the specific flavor of developer pain we are looking at today. Um, you have your application open, right?
Oh, yeah, we've definitely all been there.
Right, like a dashboard or a rich text editor, maybe an internal CMS, and you have multiple tabs of it active across your monitors. So in one tab, you update a piece of state.
Like toggling a user permission or something.
Exactly. Or, updating a nested configuration object. The UI reacts perfectly. But then you alt-tab over to another window running the exact same application, and the state is completely stale.
Just sitting there, totally out of sync.
Yeah, and it stays like that until you manually hit refresh to force a full re-render. It's just one of those jarring UI failures that instantly breaks the illusion of a reactive, modern web app.
It really is a pervasive issue. And I mean, it stems from a fundamental conflict in how modern front-end architectures handle state management versus how the browser actually handles process isolation. You expect your app state to act globally for the user, but the browser enforces strict, localized silos.
Which brings us to the core of today's deep dive. We are exploring a surprisingly elegant, built-in browser feature that developers often miss. And we're doing this through the lens of a highly entertaining piece of technical fiction by software engineer Aaron Rose.
Yes, the piece is called The Secret Life of JavaScript Crosstab Sync with the Broadcast Channel API. It is a great read.
It really is. Rose frames this complex architectural problem inside a narrative setting that is just brilliantly atmospheric.
The framing device does heavy lifting here. Instead of dry documentation, we get a narrative that establishes the stakes immediately. The source material drops us into this grand, sweeping Victorian library in London.
Yeah, surrounded by dark wood paneling and towering bookshelves. It visually represents code craftsmanship. And in this library, we meet our two engineers.
Right, Margaret and Timothy.
Exactly. Margaret is a senior software engineer. She drinks dark roast coffee and treats system architecture with extreme precision. And then we have Timothy, her junior colleague.
And Timothy is talented, he is eager, but he suffers from a very specific modern developer affliction.
Oh, absolutely. He immediately jumps to the heaviest, most complicated cloud-based solution for literally any problem.
Which perfectly sets up our technical conflict. Timothy is staring down a synchronization bug across multiple tabs, and his approach to solving it perfectly encapsulates the assumptions so many developers make every single day.
So let's dissect the bug Timothy is dealing with. He has two browser tabs open, Tab A and Tab B, sitting side by side on his monitor. He is inside his account settings in Tab A, and he decides to update his display name.
He changes it from Timothy to Timothy, Senior Engineer.
Right, a bit of aspirational UI manipulation there. He hits save. Now, according to the narrative, the application leverages the File System Access API, so it writes this configuration change directly to the local disk.
And Tab A immediately updates its DOM to reflect the new state.
But when he looks at Tab B, the profile badge is frozen in the past. It just says Timothy. Clicking around doesn't fix it. Now, looking at this, wait. If the File System Access API literally just wrote the change to the disk, why doesn't Tab B immediately know about it? Aren't they running the same app?
Well, it feels intuitive that they should share that context. But that assumes a monolithic browser architecture, which, hasn't been the standard for over a decade.
Oh, right. Because of sandboxed context?
Precisely. To understand why Tab B is completely blind to Tab A's disk write, we have to look at how modern browsers handle multi-process architecture. When you spin up Tab A and Tab B, even on the same domain, the browser isn't running them in a single execution thread.
They are completely distinct, right?
Yes, distinct OS-level renderer processes. The browser provisions separate memory heaps, separate V8 engine instances, and strict communication boundaries.
It's a security thing.
Largely, yes. It prevents one infinite loop from taking down your whole browser, sure. But mitigations for hardware vulnerabilities like Spectre and Meltdown dictate that you cannot have shared memory spaces without intense security boundaries.
Meaning Tab B has zero visibility into Tab A's memory pool?
Exactly. And it certainly isn't polling the OS file system for changes just because Tab A executed a write operation.
Okay, so Timothy realizes these renderer processes are isolated, and he decides to bridge the gap. He marches over to Margaret and pitches his grand architecture. He announces, I am going to spin up a WebSocket server on the back end.
Which is the ultimate reflex for developers today.
Totally.
Whenever we hear the phrase real-time synchronization, our brains instantly autofill WebSockets.
Well, to be fair to Timothy here, if he were building a live collaborative environment, say, multiple users editing the same Figma canvas, He would absolutely need that WebSocket architecture.
Oh, without a doubt. You need a centralized server to resolve merge conflicts in that scenario. Oh.
Right. But the trap he fell into isn't that WebSockets are bad. It's using a global transport layer for a purely local state sync problem.
That is the crucial distinction. And Margaret's response to his pitch is fantastic. She calmly breaks down the exact physical networking route of the payload he is proposing.
Oh, this part is wild. Walk us through Margaret's mapping.
Okay, let's look at the lifecycle of Timothy's WebSocket idea. Tab A registers the state mutation. It serializes the payload, triggers the browser's network thread, and initiates a TCP handshake.
Okay.
Then it establishes a TLS connection. That packet leaves the machine, hits the local Wi-Fi router, traverses the ISP infrastructure, and physically travels across transoceanic fiber optic cables.
Because they are in London.
Right.
Yeah.
So that payload goes under the Atlantic to a cloud data center, let's say an AWS region in Virginia.
Just to sync a tab on his own screen.
Exactly. And once it hits Virginia, it has to process the request, open a database transaction, and broadcast a socket message back.
Back across the Atlantic.
Yes. Back across the ocean, down through the local ISP, and finally arriving into the network thread of tab B, which, again, is sitting 2 inches away on the exact same monitor.
Okay, let's unpack this because that is insane. That is like texting your roommate who is sitting next to you on the couch, but routing the message through a cell tower in another country instead of just turning your head and whispering to them.
That is the perfect analogy. It is a massive, latency-heavy round trip for data that never actually needed to leave the local machine. Margaret captures this perfectly in the text.
Yeah, what was her exact quote?
She asks him, "Why are you routing a packet through a data center far away just to whisper a secret to a tab running on the exact same computer using the exact same memory pool inside the exact same browser engine?"
It's brilliant, and it points to a wider symptom in our industry. Developers get trapped in these default solutions.
We really do. We inject heavy network latency and increase cloud bills, all to solve a problem the browser can handle internally.
Which leads directly to Margaret stepping up to the library whiteboard. She grabs a marker, draws a thick horizontal line, and labels it Broadcast Channel.
And this is the native solution, the Broadcast Channel API.
So what exactly is this API? Because we know the tabs are isolated processes. How does it pierce that sandbox?
The Broadcast Channel API acts as a native zero-latency communication bus. It's provided directly by the browser, specifically for sandboxed contexts. It handles the inter-process communication safely without any cloud server needed.
No WebSockets at all.
Zero. And 0 bytes of network traffic generated. Tab A sends a message to the local channel, and every open tab from the same domain gets it instantly.
And it is strictly governed by the same origin policy, right?
Correct. The isolation boundary is maintained at the origin level. But if tab A and tab B share that origin, they can communicate natively. It can even broadcast straight to web workers.
Okay, here's where it gets really interesting, but surely there's a catch, right?
Yeah.
Can this thing actually handle complex data, or is it just sending basic text alerts?
That is exactly what Timothy wonders in the story, and it's a super common concern. But Margaret introduces the technical reality under the hood broadcast channel, natively utilizes the structured clone algorithm.
The structured clone algorithm. Let's dig into that, because I remember the old hack we used to use for this.
Oh, the local storage hack?
Yes. A few years ago, we'd attach event listeners to local storage mutations. Tab A would write to local storage, and tab B would catch the event and update.
It was a clever workaround, but architecturally terrible.
It was so clunky. You were basically forcing developers to write data to a physical disk just to trigger an event in the browser's memory.
Exactly. You were paying a massive performance penalty. And with local storage, you had to manually serialize everything into JSON strings.
Right, running JSON.stringify on massive nested objects.
And JSON is rigid. It drops regular expressions, data objects become strings, and it definitely can't handle raw binary data. Contrast that with Broadcast Channel, which Margaret describes as an ephemeral, purpose-built messaging bus.
Ephemeral meaning it just exists in memory. No disk writes.
Yes. And because it uses structured cloning, it can transfer native objects, multidimensional arrays, strings, all without manually stringifying anything.
Wait, really? What about binary data?
It handles that too. You can natively pass blob objects and raw binary array buffer data.
Oh, wow. So if a user uploads a high-res image in tab A, we can push that entire binary payload to tab B instantly.
Instantly. And in some contexts, with zero-copy data transfer.
That is incredibly performant. So Timothy hears this, scrubs the whiteboard, and scraps his back-end WebSocket architecture.
Rightfully so. He follows Margaret's layout and initializes a unified broadcast channel.
Let's outline the specific functions he uses. It is shockingly simple.
It really is. In tab A, when the file saves, he instantiates the channel and calls a function to broadcast the update. He just passes the state object directly into the post message method.
And over in tab B
initializes the same channel and registers an on-message event listener to catch the payload.
Now, the source material explicitly notes that Timothy ensures the event listeners are cleaned up if the tab closes.
Yes, that is a critical detail. You have to ensure garbage collection happens. If your user is navigating around a single-page app and components keep creating listeners without closing them,
you get a massive memory leak.
Exactly. The JavaScript main thread will eventually choke. You must invoke the close method when the tab or component unmounts. Timothy handles this flawlessly.
So the implementation is solid. It's time for the triumphant result. Timothy goes to tab A, deletes the senior engineer tag from his display name, and clicks save.
And the result is immediate. In the exact millisecond the local file updates, tab B silently snaps to mirror the change.
No loading spinners.
Yep.
Just an instantaneous state reflection. But the aha moment, my favorite detail from the whole piece, is what Timothy does next.
Checking the network log?
Yes. He opens the network inspector in DevTools, and the network log is completely blank.
0 HTTP requests.
Yeah.
0 WebSocket frames. Absolutely 0 network overhead.
It is so satisfying. He achieved real-time synchronization without asking the network layer to do a single thing. So what does this all mean for you listening to this?
Well, it's not just about JavaScript or this specific API. It's a reminder to question our assumptions as developers.
We really do have this cloud-first conditioning, don't we?
We absolutely do. We often reach for heavy, complex, cloud-based dependencies because it's just what we're used to. We forget to look for elegant, native tools right in front of us.
We ignore the whispered solution locally because we're busy building a megaphone to shout across the ocean.
That is the perfect way to phrase it. The elegant solution is often local.
And that leaves us with a final, provocative thought to ponder. Building on Aaron Rose's piece, if our browsers contain these incredibly powerful, zero-latency local communication channels that we completely ignore in favor of routing things across the Atlantic,
Right.
what other native local computing powers are sitting completely dormant on our devices simply because we've been conditioned to think the cloud is the only way to solve a problem?
It's a great question. When you look at local large language models or web GPU, you really have to wonder how much of our cloud infrastructure is just legacy habit.
Exactly. Something to definitely explore on your own. Next time you architect a feature, take a moment to ask if the local machine can just handle it natively.